Today we're going to be talking about introducing a little bit about chemical reactions, a review from when you guys had physical chemistry, physical science, and then we're going to use that to talk about the main topic we're talking about in biology, which is enzymes. One of the key concepts you need to realize is that chemical reactions are everywhere. They're in cooking. Anytime you brown a piece of meat, that's a chemical reaction. They're in respiration when you're breathing and actually breaking down sugar to create or to release energy to power your body. Here's an example of a chemical reaction. So we have C6H12O6 plus O2 goes to CO2 plus H2O plus heat. In words, this would read glucose plus oxygen goes to carbon dioxide plus water plus heat. This is known as a combustion reaction, where we have a sugar or a carbohydrate or a carbon-based compound plus oxygen releasing energy or heat and CO2 and water. Wait, this is saying that sugar plus oxygen goes boom. But my sugar isn't on fire. More specifically, my chocolate-covered Chex Mix isn't on fire. So why is that? When the reaction clearly says that a sugar plus oxygen should combust, why? What could possibly stop that from happening? Well, the answer to that is activation energy. An example of activation energy, or the best illustration of that, is a hill. So let's say you start out with a certain amount of energy in your reactants. So you start out with a certain amount of energy in your unburned sugar or your unburned fossil fuel, your oil, your gas. And then the end result after the reaction has so much energy. Well, notice to actually start the reaction, you first have to supply some energy. This hill is known as activation energy. This is why you need to provide a spark to cause something to ignite. So when you use a spark with a piece of newspaper, you're providing the energy required to start the reaction, and the reaction can finish out and you end up with your burnt piece of paper down here. So activation energy is the reason why things don't automatically burst into flames. You first have to provide that energy to start the reaction and get over this hill, and then the reaction can proceed. What does this have to do with biology? This is why our bodies actually need to have enzymes in it. Nothing in our body actually works without enzymes. How are they actually important? All chemical reactions in living things require enzymes to work. There's nothing in the body that could actually function without an enzyme, any reaction. So you have ones that build molecules up. So in this case, you have enzymes that are actually going to stick these two guys together, are going to synthesize products. And you have enzymes that are going to break down molecules. So in this case, you start out with this and you're going to break it down, like when you think of enzymes in your stomach during digestion. One thing I also like to mention is the reason why all chemical reactions need enzymes to work is that all these reactions would occur naturally, but they would take way too long to actually work. So what enzymes do is they actually make them go faster. As I mentioned, the thing that enzymes actually do is they speed up reactions. Something that speeds up reaction is known as a catalyst. So catalysts help reactions go, they make them go faster, and they're the reason why you're alive today. So once again, all these reactions would occur normally, but it might take hundreds of years for you to digest that piece of bread that you had for breakfast. You can't survive 100 years without energy. So we need enzymes to make those reactions go faster so we don't die by the time we digest breakfast. How do enzymes actually do their job? What they do is they lower the activation energy required for chemical reactions. We see this energy diagram, which is very similar to that hill picture I showed you earlier. We have the reactants have a certain amount of energy here. The products have a certain amount of energy here. And once again, this hill is your activation energy. So you notice originally you have to supply this much energy to get the reaction to go and create the product. What the catalyst, or what the enzyme does, is it doesn't affect the beginning or the end. All it does is it lowers the amount required to actually start the reaction. I highly suggest you copy this diagram into your notes. Hint, hint, you might see it again. So what you need to understand is that enzymes make reactions go faster by decreasing the activation energy of the reaction. Another key thing you need to understand is that enzymes are proteins. So they're one of the 4 macromolecules we discussed already. Specifically, they are proteins or made up of protein subunits. Each enzyme is specific to a specific reaction. So there's enzymes that will only work on one type of reaction, and there's a reason for that. The reason for that is that each enzyme needs to be the right shape for the job. So we mentioned with proteins how each protein has a specific 3D shape. Well, this is one reason why it has that 3D shape, is because if it's an enzyme, if that pocket is the wrong shape, the enzyme cannot function and the reaction cannot work. And if the reaction doesn't go, possibly you could die, possibly you might have something like lactose intolerance and you can't drink milk. It all depends on what enzyme is the improper shape. Enzymes are named for the reaction they help. So we have sucrase, it breaks down sucrose, which is table sugar, white sugar. We have proteases, which break down proteins. We have lipases, which break down lipids. And we have DNA polymerase, which builds DNA. And you should notice at the end of all of the enzymes, it ends in ase. So anything that ends with ase at the end is an enzyme. And what it breaks down is told by what's beginning. So protein, protease, very similar. Lipase, lipid, very similar. I hope I hammer this point home. It's the shape that matters with enzymes and with all proteins in general. The current, or one of the models of how enzymes actually work is known as the lock and key model, where you have the lock, which is your enzyme, and the key is your substrate or the reactant of the reaction. So the lock and key model says that the substrate, which is the reactant, can actually fit in the key spot on the enzyme perfectly. So because it fits, the reaction will go and the products will pop out. Once again, just like you have a specific lock with a specific key, the same exact thing. This pocket will only fit this substrate. If another substrate tries to fit in there, it can't fit, the enzyme will not have, or the reaction will not go. Enzymes are not used up in reactions. In general, catalysts are not used up in reactions, so you don't need a lot of enzyme to actually get them going and keep them going. Enzymes are not changed, so there's no damage done to the reaction, so that once this reaction down here occurs, this enzyme can just be recycled over and over and over until eventually it will fall apart, but it's not a one and done deal. They're used only temporarily. I mentioned they can be reused again and again for the same reaction. And it's very little enzymes actually required to get them going. Because you can keep reusing it, you don't need to have an overabundance of enzyme to get the reaction going. Once again, vocab, you have the substrate, which is the substance that the enzyme acts upon. You have the enzyme, which in this case is this guy down here. A new part of the enzyme, which we didn't talk about, is the active site. The active site is the area on the enzyme that the substrate fits into. So you can see right here is the active site. That's why the substrate fits in there. That's where the reaction actually happens. That's why it's known as active. And then the final thing is the product, which pops out after the reaction is over. A review of the vocabulary. The enzyme is the actual helper protein molecule. The substrate is the molecule that the enzyme works on. The product is what the enzyme helps produce from the reaction. And then the active site is the part of the enzyme where the substrate actually fits into. So the substrate fits into the active site of the enzyme, creating the product, whatever that product is. We talked about how enzymes work, what actually are the main jobs of enzymes. Now the question is, what actually affects enzyme action? So what can cause enzymes to either not work properly or to work better? They are temperature. Why? Enzyme has to be the right shape, as we mentioned, which I'll go into more detail about temperature in a minute. pH, which is how acidic or basic it is. Why? Because the enzyme has to be the right shape. Again, pH can affect the shape. The amount of enzyme, which should make sense. The more enzyme, the higher the reaction. higher reaction. And you also have the amount of substrate. The higher the substrate, the higher the reaction, and vice versa, up to a certain point. At a certain point, if you have so much substrate and not enough enzyme, all the pockets are filled up anyway, so you can't go any faster. Let's go into a little more detail about how temperature actually affects enzyme activity. The reason why, or I should say, each enzyme has something known as an optimum temperature. Optimum meaning the best temperature it actually works at. This is what causes the greatest number of collisions between the enzyme and the substrate. In anything that has a temperature above 0 degrees Kelvin, so anything that has a temperature above negative 273 degrees Celsius, has molecules that are moving around and banging together. At this optimum temperature, you have the molecules of the enzyme banging together with the molecules of the substrate, causing the greatest number of collisions. So at this temperature, they're hitting each other the most, so they're fitting into it better, so they are going to cause the reaction to actually speed up and go the quickest at this temperature. What happens when you actually raise the temperature? You do something known as denaturing the protein, which is another vocab word. When you denature a protein, it unfolds and loses shape. So when you overheat enzymes, you can cause the protein to unfold and relax. If it loses that shape, it can't work anymore. So it cannot work. That's why it's dangerous. If we overheat your body too much, your enzymes will not function anymore and you'll die. If we actually decrease the temperature, decreasing the temperature doesn't do anything to the protein itself. What it actually causes is, instead of banging together very quickly, it causes the molecules to move much slower. So you don't have as much collision. If you don't have as many collisions, you don't have as much reaction rate. So higher temperatures cause the enzymes to actually unfold. Lower temperatures just cause the collisions to be less common, so the enzyme doesn't work as well. Let's show a graph showing the effect of temperature on an enzyme. Here we have human enzymes. We can clearly see that we have temperature. We have temperature on the x-axis. We have reaction rate, or the speed of the reaction, on the y-axis. And we can see that as we increase the temperature of the human body to a certain point, the reaction rate keeps increasing. At 37 degrees Celsius, which happens to be human body temp, we see that we have the highest reaction rate. Then after, if you have a fever, or we start heating you much above body temperature, we can see that the reaction rate starts to decrease. Eventually, it's not going to work anymore when all the enzymes become denatured. So here is where that optimum temperature is. Optimum temp. It's that temperature where we have the highest reaction rate. And here we have denatured enzymes. The second one I want to discuss is pH in more detail. Once again, what pH does is it actually denatures enzymes also. So when you change the pH of a solution or of your body, if you make it too acidic or too basic, either way, it's going to affect the bonding that's actually occurring inside the enzyme, and the shape will change. If the shape changes, the enzyme can't function anymore. The enzyme can't function anymore. The reaction rate is going to decrease substantially. Most humans have a range between pH of 6 and pH of 8, because that's about the normal pH range found in your blood. But it really depends on where in the body. So pepsin, which works in your stomach, likes a pH of 3 because your stomach's acidic. Trypsin, which is an enzyme that also breaks down proteins, which works in your small intestines, however, is a pH of 8 because your intestines are actually slightly basic. So they're more basic than your stomach. So things that work in your stomach will not work in your small intestines, as we'll see. Here we have another graph. Instead of graphing temperature on the x-axis, we have pH, and we still have reaction rate on the y-axis. We can see here's one enzyme that is just occurring in your blood, we can see that it has an optimum pH of 7. So it works best at a pH of 7. Anything less than that or greater than that, and it doesn't work as well. Stomach pepsin, we can see we have a similar shape graph, but we notice that it's shifted all the way to the left. Here we have an optimum pH of about 2.5. So pepsin works best in a pH of 2.5. Anything to the left of that, anything to the right of that, and it's going to denature. The last example, we have trypsin. We can see trypsin is the curve is slightly to the right. In this case, the optimum pH is at 8. Optimum. So here, when you get up to 10, the protein denatures. And when you get below 5.5, the protein also denatures. So the key concept I want you to understand here is that every enzyme has a different optimum pH. And if it's not at its optimum pH, it's not going to work its best. So it's not going to cause the reaction to go as fast as you might need it to or as you might want it to. For enzymes, what matters? You should all have an answer for this, and the answer is the shape. Thank you for watching, and please bring your notes and any questions to class.